The Irrationals, Pi. In the last video, we discussed the irrationals found when taking the square root of a non-perfect square number. The essential point could have been worded as follows. If irrational numbers do not exist, then every number ever must be a perfect square. The idea being that in a universe where irrational numbers don't exist, every number would be the product of two equally valued smaller integers, such that 2 would have to be the product of two smaller whole number integers. So if we stop pretending that irrational numbers exist, we'd then have to stop believing in the number 2. Or we would have to invent a whole number that exists between 1 and 2, essentially making a new 2, call it oot, such that 2 equals oot times oot. More realistically and objectively, irrational numbers exist because 2 exists as a whole number between 1 and 3. Irrational numbers do not exist in reality as the number 2 does not exist in reality. The concept exists in reality. The idea works for us humans, as we are difference detectors. Both the counting numbers and the uncountable numbers are valid applications for and about reality. Irrationals are just higher up the abstraction chain. 2 is valid and means an individual unit of a group and another individual of that group. The group may be specific, like golden delicious apples from the oldest tree in the Albion Orchard at Innes Lake Road in Ontario, Canada, or as general as objects in the universe. Either way, 2 means 1 and 1 members of a group. So the first abstraction is the similarity that makes a group. Following that, there comes the number 2 as a specific concept of the certain number of members in that group. Then comes the idea that we can find which quantitative number concept we will have if we want to double or triple or increase by x a group of more than 1. This multiplication trick has special cases where the group size is equal to the number of increases of that group size. The multiplication of 2 equal values makes a square. Pretending every number is a square results in roots, which cannot be written as a whole number, or as a ratio of 2 whole numbers. This is when the abstraction of irrationals must appear. Okay, so irrational numbers are valid conceptually, and they appear when you attempt to apply the higher level concepts of multiplication of equal values, otherwise called powers or exponents, to lower level concepts like 2. In this sense, we can never really make a square with an area of 2, as the length of the side would have to be irrational. We can, however, get close enough to 2 units squared to make it indistinguishable for humans. But are irrationals just leftovers after accounting for the whole numbers and rationals? Maybe, but let's see where else irrationals appear. If we move from squares to circles, we can find the irrational number pi. Pi is most simply defined as the result of the ratio of the circle's circumference to its diameter, and we write pi equals c over d. Pause. In the last video, we said that the square root of an integer n, which is not a perfect square, is irrational only because it cannot be written as the ratio square root of n equals p over q. This gave us the square root of n is not equal to p over q, therefore the square root of n belongs to the irrational numbers. So how can pi be equal to c over d and be irrational? The answer is in the type of ratio. P over q was made of 2 integers, and that's what we call a rational number. Is c over d a rational number? The diameter, a straight line that cuts the circle in half, can be defined by an integer. Say you have a ruler, a yardstick or a meter stick, whatever. The ruler has a whole number length, in whatever unit it uses. Now, you cut a hole in the exact center and place that ruler on a pivot. You add a short stick on one end of the ruler and another on the opposite side. The sticks make contact with some sand evenly, flatly spaced under the ruler. You spin the ruler and a circle is produced by your action. Is the measure of this line in the sand a rational number? We could rewrite the pi equation for the circumference. C equals pi times d. Without numbers or sets, this equation still has some physical meaning. It means take a straight line of a finite length and rotate it around an axis found in the midpoint of the length. Rotate it such that the two ends swap sides. The combination of the two sweeping ends will create a circle. Okay, so we have a circle. What's its length? Length is a measure of distance. So it's technically the length of the ruler, but it's the length of the ruler in multiple directions at once. We could either wrap something around the circle, like a rope, and then straighten the rope out into a line to measure. Or we could roll a steady circle like a wheel and measure the distance in one turnover. In either case, you will find that the circumference is about 3.1 times larger than the diameter. The more accurately you measure, the more numbers you add to the value of pi. 3, 3.1, 3.14, 3.141, etc., till you get some long number like 3.14159265358997, and so on and so on. But you can always add a new number to the end by finding a more accurate approximation. This is because pi is irrational, which I will leave Mathlogger to show you. I want to look at the circle more than the evidence of the mathematical manipulation. The reason pi is irrational is because circles cannot be measured without involving straight lines. Whether we wrap a string around that sand circle or make a wheel, the string and the wheel are discrete at the smaller levels and are not creating a perfect circle, but rather a shape with straight lines in the material or in the material of the measuring device, an n-sided polygon. The most perfect circle I could think of might be a ripple in a pond from a droplet falling straight down on still water. The water, however, is composed of dihydrogen monoxide, which is discrete, so the ripples may not be perfect. Even if it is, it's going to be hard to measure the circumference of a moving, growing circle. Shapes are an abstract idea. Even a straight line is an abstract idea based on very, very strong candidates, which are, to our eyes, real straight lines. But as we pull out a microscope and recheck, everything gets bumpy eventually. So back to the question, why can pi equal c over d? Because circles are abstractions of a shape without straight lines, while being itself a straight but curved line. If you make the diameter a whole number length, which you cannot do in real life, but you can get close enough, so let's say you make the whole number length even abstractly, you have to rotate it about its center, and the circumference which is swept out is an abstraction, which at its atomic level is not a perfect circle. So the measure must be irrational. If you use an irrational diameter, which can only be done abstractly, then you could abstractly make the circumference rational. But pi would still be irrational. A rational number over an irrational number is still irrational. You could also have an irrational diameter and an irrational circumference, and pi would still be irrational in that case. Although being an irrational like the square root of 2, pi is different from irrationals like the square root of 2, as pi is transcendental, whereas the square root of 2 is algebraic. An algebraic number is any complex number that is a root of a non-zero polynomial in one variable with rational coefficients. A general example may look something like this. A over b times x squared plus c over d times x plus e over f. The square root of 2 can be found in looking for the root of 1 over 1 times x squared plus 0 over 1 times x plus negative 2 over 1, which simplifies into x squared minus 2. If you solve for x by setting the polynomial equal to 0, you get x squared equals 2. Taking the square root of both sides, you get x equals the square root of 2. Therefore, you can find the square root with rational numbers using algebra. Pi cannot be found in this fashion, as pi is transcendental, which means not algebraic, which means pi cannot be found with algebra. Neither can Euler's number e. So we will talk a little bit more about transcendentals and Euler's number in the next video. Don't forget to like, comment, share, and subscribe, and support us at patreon.com/youexist.